Hi, I'm John Arno. I'm a professor in Earth and Space Sciences at UCLA, where I teach Intro to Oceanography. Today we're going to show you a number of films showing analog experiments that demonstrate the types of dynamics and flows that you can expect to see in Earth's atmosphere and oceans. It's somewhat hard to understand the effects of rotation on fluid motions, so first we're going to start with some simpler experiments where we just roll some ball bearings across a table that is rotating at different rates. We're now going to do experiments using our rotating table. It's about 1 meter in diameter, and I'm going to roll balls down that little ramp. And when the table's not rotating, the ball will travel straight across. When the table rotates, the camera, which is affixed in the rotating frame, will see the Coriolis deflection of the ball. It deflects off to the right when I move the table in a right-handed sense. Now by hand I'm going to move it to the left, and you'll see it's going to deflect the other way. Now we're going to use the motor on the table to rotate it at a constant rate. And what you'll see is the faster the table rotates, the more Coriolis deflection the ball feels. So at 4 RPM, you see the ball deflects a little bit. Now we'll increase the rotation rate to 8 RPM, and the ball will be deflected more. And it does. It's deflected about twice as much. Lastly, at 12 RPM, the ball's deflected even further to the right of its intended path. In a right-handed system that's rotating counterclockwise, the deflection of the particle is off to its right. Furthermore, we see that the strength of deflection increases with the rapidity of the rotation of the system. Now let's do a thought experiment to try to understand how Coriolis varies as a function of latitude over a planet. Let's put a table similar to the one we were just rolling ball bearings across, a big version of it right at the North Pole. You can see it looks a lot like the setup we have. The rotation axis is going straight through the center of the table, and it's perpendicular to the table. So gravity points everywhere inward on the planet. It'll always hold any ball bearing I roll across that table on that horizontal plane. And so when I roll it down the ramp, it's going to get deflected off to the right by Coriolis effect. If I put a similar table in the mid-latitudes, then now you can see the rotation axis, the Earth is still rotating around the same axis, so the rotation axis is still pointing in the same direction, and the table now appears tipped because it's locally perpendicular to a different part of the planet in the mid-latitudes. So if I break up the rotation axis into two components, one shown in red, one in green, the red lies in the plane of the table, green is perpendicular to the table. The red component is ineffective because the ball bearing can't come on or off the table due to gravity. So it doesn't get deflected vertically. The only deflections are horizontal, and only the perpendicular green component of the rotation axis will act to deflect the ball horizontally. So there'll still be a deflection, but it'll be a bit weaker than at the pole. If we put another table in the equatorial plane, then you can see now the rotation axis lies perfectly aligned in the plane of the table. So there's no Coriolis deflection of the horizontal motions of the ball on that table. Lastly, if we put the table down at the South Pole, you can see the table is now so-called upside down with respect to the rotation vector. The rotation vector now points into the table, whereas at the North Pole it's pointing out of the table. So there's still a very strong Coriolis deflection there, but it's left-handed now. It's off to the left instead of off to the right. So Coriolis goes from strong at the poles to zero at the equator to strong again at the other pole. And in the experiments we'll show from here on out, we're not actually going to take into account the variation of Coriolis as a function of latitude. Instead, you can think of all our experiments as occurring at some latitude away from the equator where Coriolis exists, and for our intents and purposes, it's roughly constant. In the next set of experiments, we're going to consider how a planet's atmosphere circulates and overturns in time. Now let's try to understand the basic circulation occurring in Earth's atmosphere. The atmospheric circulation is driven by a difference in heating at the equator versus at the poles. On average, the poles are colder than at the equator. And in most textbooks, you'll see a cross-sectional view of the atmospheric circulation that looks like this slide. There's a polar cell, then a ferrule cell in the mid-latitudes, and then an overturning Hadley cell nearest to the equator. There's another set of these in the southern hemisphere. Today we'll take a northern hemispherical viewpoint of the planet. We won't discuss those in detail. And what we will discuss is that if we look on the surface of the planet in map view, that affiliated with each of these cells is an east-west wind belt. The Hadley cell has the trade winds going from east to west. There are the westerlies in the mid-latitudes and the polar easterlies at higher latitudes. And we'll now try to build some simple lab models to understand what could cause these types of circulations. And in fact, what we'll really show is that we can build a pretty good model of the Hadley cell. The ferrule cell and the polar cell are more complex than what's in the books. And we'll discuss that a bit as we go. So we're going to start out with a very simplified model. We're just going to study a channel model of the atmosphere. Now let's try to understand what's going to happen on a non-rotating planet. We're still going to assume there's cold material at the poles, warm material at the equator. This will tend to drive a large-scale overturning circulation from the poles to the equator and back again. The cold material at the pole sinks down, coats the surface of the planet, heads from pole down to the equator. Meanwhile, the low-density, warmer material at the equator floats up, hits the top of the troposphere, and is going to spread out towards both poles. A point of convention, all the superficial flows along the planet's surface are demarcated with solid lines, and all the flows at the top of the atmosphere are always marked by dashed lines. So now if we look in plan view down on this atmospheric overturn, we'll see surface flows going from pole to equator and flows at elevation going from equator to pole. We're going to take a narrow slice through this atmosphere. We can't make a whole planet, but we can do a little channel experiment where we try to take a pole to equator slice. And we're going to do that in the lab. Let's see how it works. The experiment here has blue denser fluid at the North Pole on the right and yellow less dense fluid on the left at the analogy to the equator. You could see the blue denser fluid sinks to the bottom of the fluid layer and spreads out, coating the bottom, and thereby heads from North Pole towards the equator. In contrast, the less dense fluid at the equator floats to the top, coats the top surface, and travels from equator to pole. And this is our analogy for a large-scale overturning atmospheric circulation. In the present experiment, we're going to use that same channel setup using the same tank as before, but now we want to investigate what happens in a thin channel like this if we allow the planet to rotate. So we now have a setup where we've put everything on a rotating table. Okay? So now the whole system rotates. And when I mean the whole system, that means we have the side view camera in the rotating frame. We have the top view camera as well, situated in the rotating frame. This big table is driven by a motor beneath it, and so we can set it to rotate at a constant rate, just like a planet. Okay, so now to simulate dense fluid at the North Pole and warm fluid roughly at the equator, we have blue dye. It goes into the tin can over there, and the yellow or orange low-density fluid goes into the can over here, and John Cantwell has set up a system whereby a weight over there pulls the two cans up at the same time in the rotating frame. We can now no longer reach in and do it by hand. We would get injured. We just saw in a non-rotating experiment that the flows linearly travel from pole to equator and from equator back towards the pole. Now, if we worry about a rotating system, then there'll also be Coriolis deflections of the motions such that flows heading from pole down towards the equator will be deflected off to their right, and therefore they'll get deflected off towards one side of the tank, and the flows heading from the equator up towards the pole will be deflected to the other side of the tank. Let's do this with the exact same channel and see if we can see that deflection. You can now see that we have the exact same setup as before, but the whole setup is now placed on our rotating table. We pull up the containers and release the die, and in side view we see roughly the same overturning circulation. But in top view we see a significant difference. Now the flows are deflected to the right of their intended path, so they're each hugging one side wall, as we predicted based on the effects of the Coriolis accelerations. Our last experiment was looking at a very narrow channel. Now let's try to open up the sides of our box a bit. The first issue is there are no boxes in the atmosphere. So we really want to make the box as big as we can. So the channel worked fine to get a first look at things, but now let's see what happens when we open things up a bit. Another issue we have in this experiment is that we can only put in blobs of dye. So this time we'll put the blue dense dye in the northeast corner of our box, as shown in the slide, and the low density yellow material down in the southwest corner. In a non-rotating experiment then, what you'll see is that the dense blue stuff will coat the bottom and spread out from the northeast corner, and the yellow stuff will rise up and spread out from there. It's still basically a classic overturning cell when seen in cross-section, and it'll be a little more interesting than that seen in plan view. Let's run it. You can see we released the die. The blue and yellow each spread out from the corner they're initially in, and they coat each of their respective surfaces. You can see the blue dye reflects off the sidewalls. We've done the non-rotating channel tank, in which the fluid just spread across from one side to the other. We did a rotating version where it got deflected and stuck onto each sidewall. Now, as you can see behind me, we've got the whole system rotating again. We've got the square tank in there, and we're going to do the same experiment again. In the non-rotating square tank, again, the blue dense fluid sank to the bottom and spread out and coated the bottom. Now in the rotating system, I think we're going to see a different behavior. Again, it's going to get deflected way off to the right, as we would expect in a system where rotation really matters, such as a planetary atmosphere. So there we pulled up the containers. The blue and yellow dye tries to spread out, but instead it's massively deflected off to the right of its intended path. The two previous atmospheric overturn experiments we did used tanks that have sidewalls that interacted with the flows. In a sense, those are both incorrect. The atmosphere doesn't really have sidewalls. So the last experiment we're going to do, we're going to take off the square tank, and on our rotating table, instead, we're going to put, let's say, a circular tank. And you could imagine there being a circular tank right here at the pole, right? And so there are sidewalls, but they're encircling a line of latitude. And what we're going to do is we're going to put just a patch of cold, dense fluid right in the center, and we'll see how it responds in a non-rotating experiment, and then again, as always, in a comparable rotating case. John Cantwell is about to pull the cylinder, releasing the dense, in this case, green dye. The dense stuff, maybe not surprisingly by now, sinks to the bottom and spreads out, coating the bottom of the tank pretty much uniformly. Now we have a rotating experiment. Same deal. The die does not sink. It does not uniformly coat the bottom. Instead, it forms actually a pair of vortices, and that pair of vortices propagates across the tank as a coherent unit. Very, very different response than in the non-rotating experiment. Let's now synthesize the experiments that we've just done to try to discuss and understand the standard image you see in textbooks of the atmospheric circulation. Typically what you see is that there's a Hadley cell at low latitudes. The Hadley cell is from about the equator to 30 degrees north. The sun is mainly driving this with heating at the equator. And the surface flow then is coming from about 30 north back towards the equator. Associated with that southward flow is a Coriolis deflection from east to west, off to the right of the intended path of the surface fluid. Near the pole, you have a polar cell going from the pole down to about 60 degrees north. The fluid is again traveling from north to the south, and it is again deflected by Coriolis off to its right, so again you get easterlies. The ferrule cell lies between these other two. It's not directly driven by a very cold north pole or a very hot equator. So the idea is that it's a ball bearing between the other two. Therefore, its motion is reversed. It's being spun by the other two cells. And so the surface flow then is actually from the equator towards the pole. And when this surface flow is deflected by Coriolis, it's from west to east. Okay, so you have two easterlies. In between them is the mid-latitude westerlies. The argument is it's due to these three overturning cells, but in all truth, recent data over the last couple decades shows no polar cell, no ferrule cell. And instead, really what's happening is there's a nice overturning Hadley cell. That idea holds up. Our experiments work perfectly for that. And in the mid-latitudes and near the poles, it's more the interaction of storms and eddies that still are strongly affected by rotational effects, as we saw in the last experiment we did in the circular tank. And those interactions between those complex eddies then lead to the polar easterlies and the mid-latitude westerlies. In the past decade or so, we've located patches of garbage near the center of each of the ocean gyres. Let's see if we can build some simple lab models to try to explain them. Okay, we're going to use the model we have of the wind belts to drive motion in a simple model of an ocean basin. And so instead of actually having wind belts, what we'll have in the lab are fans, and those fans will blow roughly in the same direction as the wind belts. And if we put garbage in here, some floating detritus, which is what we'll do, in a non-rotating tank, they would just follow the fans. But when we add rotation, there'll also be some net deflection off to the right, what's called Ekman transport. So the detritus will tend to, on average, after a while, get pushed into the center of the tank and will form a patch of garbage. That is the fundamental idea. Here's our tank viewed from above. We've got a bunch of styrofoam floating on the surface of the water. We've got a couple of fans. The fans, when we turn them on, blow the garbage around in a circle. In a non-rotating tank, not surprisingly, the floating stuff follows the wind. Now, when we rotate the tank, we get a different behavior. We'll speed up the rotation rate so this all happens faster and so that we all get dizzy. And you'll see the garbage in time will get deflected in towards the center. And eventually, all this garbage will form a patch relatively close to the center of the tank. This is similar to what's happening in Earth's oceans. It's due again to Coriolis deflection off to the right of the direction of the winds. Now we're going to try to understand gyroscopic phenomena. If it's not spinning, when you let go, it falls over. When you spin it, the gyroscopic forces hold it up and it doesn't fall. Now let's redo that type of experiment using tanks of water. We're going to first do an experiment where I just take a packet of creamer, half and half. This is colder and denser than the water in this tank. And this dense creamer is going to sink. Dense things sink. So this is going to sink through the water, and we're going to see how it does so. Now what you see is that the creamer quickly falls through, forming a dense, turbulent plume, hits the bottom, and immediately spreads out. It looks somewhat like an inverted mushroom cloud, because it is. You could think of that creamer as forming a central column of denser material surrounded by the lower density water. The pressure at the base of that higher density column is then higher than in the surrounding low density water. There's nothing to support that higher density column in that high pressure region, so the fluid pushes out from the high pressure zone, coating the bottom of the tank. So now, to compare what we saw in the non-rotating tank to a case where there is rotation, we've set up a record player, as you see here, and we've got a comparable tank of water on it, and we've let that tank of water spin up so that all the fluid is moving at the same rate as the record player. So all the fluid mechanics knows about the rotation of the table. And now we're going to do the exact same experiment where we pour in the creamer. And what you see is a different behavior. The fluid this time forms an axialized column. All the fluid motions are aligned with the rotation axis. The fluid isn't falling very fast through the layer, and now that column starts to break up into sub-columns. And it eventually breaks apart into these different units, but all of them are each being held up basically by the Coriolis acceleration. If we rapidly rotate our tank of water and again pour in the cream, we'll form a column similar to the first experiment, but rotation now acts to support that column of fluid, almost as is. We still form a high pressure region at the base of the cream, but when that fluid tries to push out from that high pressure region, Coriolis wraps the fluid around the column, always to the right. So as it tries to diverge, it gets wrapped clockwise, and that clockwise flow is then deflected again by Coriolis back towards the center, back towards the high pressure region. Effectively, you support the column with this circulating flow. Something similar happens at the top. You get a clockwise, counterclockwise flow that pulls out, also helping to support the column. So in rapidly rotating systems, you can support a column of dense dye, which is incredibly non-intuitive and I think incredibly interesting. In almost all geophysical fluid dynamical systems, we see swirling flows. These are called vortices. And we see them in Earth's atmosphere, such as hurricanes, and we see massive vortices on Jupiter, Saturn. Almost everywhere we look in geophysical systems, we see these fabulous vortical structures. We're going to do some simple experiments to try to get a first-order feel for how they behave. So for our non-rotating experiment, we've put some potassium permanganate here at the bottom. Now we're adding some blue food coloring, some green food coloring, and some orange food coloring. We're going to flip a little plastic flap there on the left side of the tank, right there, right at 9 p.m. There's the flap being flipped. That builds a vortex. We'll now speed up the speed of the movie so we can see it. And you can see it's strongly three-dimensional. There's tons of turbulence inside there, and it's quickly mixing together all the different colors. And that kind of a strongly three-dimensional, highly turbulent vortex is somewhat comparable to what you see in a hurricane. In a rotating experiment, when rotation dominates, the flow becomes very well aligned with the rotation axis, as we saw in the creamer experiments. And then it's very hard for the dye to mix three-dimensionally. So if you put in a couple of patches of dye, as shown here, they'll get drawn by each other horizontally, but they won't mix fully in 3D. So in time, you'll get these amazing filamentary structures that are strongly sheared out, but you won't get full 3D mixing. Now let's redo that experiment with a rapidly rotating table. We add the purple potassium permanganate, the honeycomb pattern there is evaporative convection, and now we add a couple more colors comparable to the other experiment. And here we go, flipping the flat. In the non-rotating experiment, the strongly 3D turbulent vortex quickly mixed all the colors together into one patch. In contrast here, you see numerous coherent vortices and very long filamentary structures. The colors are pulled out, but they're almost never mixed together. And this is because all the structures in this flow are aligned along the rotation axis, just like we saw in the rotating creamer experiment. So these aligned structures have trouble mixing in 3D because they're largely 2D structures. Therefore, the dye doesn't really get mixed very efficiently, and you get these big, beautiful vortices. Now we've just tried to mix them again. We flipped the flap as hard as we could in the other direction to try to mix the colors together, to try to force mixing. Maybe there was a drop of mixing, but for the most part the yellow is still separated from the green and the blue, and we've now formed a very large purple vortex, and there were shear instabilities around the edge of that vortex, producing a number of satellite vortices around its rim. John Cantwell just added some blue dye, and you could see in this oblique view that the dye quickly forms an axialized tower, and you get a curtain of dye that also is largely 2D and gets sheared out by the vortex flow into a big spiral arm. Showing that again from above, we just see the dye shearing out, not mixing very efficiently. Now we've largely failed at mixing the colors together in the rapidly rotating experiment, so lastly we're just going to take a paddle and just paddle it as hard as we can. And that's the next thing we'll see. There it was. We did that as hard as we could to try to mix all the colors together. Maybe there was just a little bit of mixing, but for the most part you just see strongly turbulent yet rapidly rotating vortical flows. You get large-scale vortices with an amazing amount of filamentary structure, a lot like what you see in images of vortices on giant planets. I hope that through the basic laboratory analog experiments that we showed today, that we've built up some intuition for how fluids exist in non-rotating settings and in rapidly rotating situations such as apply to Earth's atmosphere and ocean. And in doing so, I hope the complex fluid dynamics that occur in the atmosphere and ocean have been made a bit more understandable.